the theorem that we started last time. Yeah, an important one. Okay, so it's strictly speaking, we have been doing just the analysis, collecting information, definitions, theorems, and trying to come up with ideas of how we actually get from point A to point B. Okay, so that's normal. Okay, so you don't know how it's going to happen. Of any complexity of the theorem, that part is inevitable. So then you produce something that might be like 3 times shorter than you have written so far. Okay, so let me review what we have done. The theorem is square root of 2 is irrational. Okay, so we have, what I did first is I tried to put it sort of translated to begin with from words to more logical statements, which also required me to introduce a variable that stands for that number that we're talking about. So even though we're talking about the specific number square root of 2, but it's still a good idea to give it a name. Okay, like you're doing word problems, in calculus, and then there are words, and then your next step is let x stand for this, y stands for that, and then you also take all the relations that you have there. I don't know, there you might remember problems like find the rectangle of the largest area when the perimeter is equal to 40. Okay, so what do? You say, well, let the rectangle have side y, side x, side y, and then you also read those words, and you read the relation between them, so you know that x 2x plus 2y is equal to 3 or something like that, and then you want to create the area, which is x times y, and you maximize it. Okay, so that's not dissimilar from what we do here. So once again, it is very nice when you can state a theorem in the form of which is entirely verbal. Okay, it just nice, feels nice. So square root of 2 is irrational, very short, and can be spoken quickly without any letters. But ultimately, if you're doing a proof, you probably will need them. Okay, so that's the relation. Square root of 2, then it's irrational. That's how far we got. We choose to go with the proof by the contrapositive, so to demonstrate that there are no such p and q, that p divided by q giving me square root of 2. Okay, so that's through the logic. It's equivalent to the original. Okay, and then what we did is we started to shake the tree. So we ended up with what amounts to an equation, right? So it's an equation, and usually when you're solving an equation, you want to find the answer. We are doing almost the same thing, except we know that what we want is the opposite. This equation has no solutions. That's what we want to demonstrate. So if you want to think of this as an equation, so what we're saying is that this equation, with respect to PQ, has no solutions. Or at least that's our claim. That's what we want to demonstrate. So sometimes no solution is just as important as productive as there is a solution. Okay, so then we did some algebra, very elementary algebra, just squared and then just multiplied by q squared, producing a new equation. So one equation, the other equation, just same pretty much equation, just simpler. Okay, so that way you don't have to think about rational versus irrational now out of the picture. There's no division also left. So square root is gone, division is gone. If you can do that, that's always helpful. And then now we came up with that idea based on our some experience with integers and factoring integers throughout these couple of weeks, that to realize that the number on the left is even, and then the number on the right would have to be even. Okay, and not only that, then we conclude that so p squared is even, as you can see, but also p itself is even. You cannot have number that is not even squared produces even number. Okay, so that's what way on the right. That is the lemma. That is nice to state because it is in fact a kind of a theorem that is you should be able to prove pretty easily. But it is just stepping stone, right? So and then we are that gives an idea that there might be a problem here. We don't even know yet, but it gives an idea that maybe there's a problem. Meaning we want to have a problem. We are trying to arrive to a contradiction. So we were looking at this equation and want to see what is wrong with it. So if there is something really wrong with it, then we've proven that it's impossible. Then there's no solution, and we're done. Okay. So then we were still going with that idea. So p is even, p is 2n. Then for some integer n, they're all integers here. Okay, and then once again we end up with we substitute, and then we simplify once again. Once again we simplify, and this is where we are at the very end. What we reached this point last time. We divided them by 2 one more time, and we arrived to a new equation which looks very much like the last one. Compare those two. Right? You see the comparison? It's almost identical. So there's 2 squares of integers on left and right, and there is extra 2 there. Okay? So it might sound like bad news because we used we had a good idea, we used it, and then we are at this place which is almost exactly the same as before. So why is it not a bad thing, but it's a good thing? It might not be quite obvious. So why do you think we have made progress?
Well, we found out trying to simplify that equation.
Yeah. Okay. So and then we didn't. Turns out it looks exactly the same.
Right. So it keeps looping, so you can't simplify it down.
Right. So it doesn't simplify.
So
there's a hidden progress there. You see what has happened? We want to demonstrate that there is no solution, and now we know that if we can demonstrate that the loss has no solution, then the previous one also has no solution. So that's all good, but the equation looks exactly the same.
And they're equal?
No, they're not equal. But the point I was making is that I stated the form of a lemma right there. So we could do it again, which is certainly we can. But that over there I have it here. That if p squared is even, then p is even, and we are continue in the same fashion. So once again, we can say that look at this picture: q is even. 2n squared on the right is even. Then q squared is even. Then q is even. We can once again express q as 2m or something like that. Then cancel 2. But why would we do it if we know we're going to arrive with the same exact place? Well, let me carry it out. Why not? Q is even by the same logic. Okay, so Q is equal to 2m. Substitute. Once again, m is an integer. Okay, so I substitute. So what do I have? I have 2m squared is equal to 2n squared. 4m squared is equal to 2n squared. Cancel 2. So once again, this is if and only if once again entirely. So I have 2m squared is equal to n squared. Look at it. It's once again same type of equation. 2 squares on left and right, and then extra 2 there. Okay. So which means that we can do this again. I would do it again if I just knew why. Why would we do it? Why there is a progress there? So it's becoming repetitive. So where's my pink? So once again, same type. It's not the same equation, right? The different numbers are now involved, but it looks the same, and we could carry out that logic again, that operation. Substituting, see, we discovered now, what's the conclusion now? What the conclusion do I draw about this equation, the last one? N is even, N is equal to 2k, I substitute, cancel 2, and I'm getting a new equation with respect to m and k this time. Okay, so why do I want to do it?
So no matter what integer you substitute in, you get the same equation.
Well, I mean, if I first I identify that the one on the right, on the one side there is no 2, which means that that number has to be even. Okay, so I substitute 2, whatever, there, and I end up in the same place. And so why? Because when I square, I have an even number with a 2 there I have 2 2's, and I have 1 2 on the right. So I will cancel, and then so 2 here, 2 2's here, and 1 2 there. I cancel, and I still have 1 2 left. And so no matter how many times I'm going to make that, I'm going to have mismatch of the number of 2's, and we'll keep going. Well, we are not dealing with the square root of 2 anymore. This is it. So we would like to arrive at a contradiction, and I say we're making progress. Do you see with the progress? Just look carefully. What is the progressing from say with the last step? I progress from Q to M. Why is it a progress? What's the difference between the Q and M? Yeah, okay.
I think it's the same thing. I don't know.
No. M, it's verse M is smaller.
Okay.
M is smaller. Than N, that's right. So than Q. M is smaller than Q.
How is it?
Is it small? Well, but multiplied by 2, it is small, right?
Yeah.
Right, so Q is twice M, which makes Q larger than M. M is smaller than, right?
Yeah.
And that happens every time we carry out this operation. We have the same logic as over here. I had an N. Where's that? Over here, once again, N is smaller than P.
Yeah.
Okay, so M is smaller than Q, N is smaller than Q. If I repeat this operation, I will get smaller and smaller numbers every time. So why is it good?
Never end.
Well, that is the question.
Will eventually converge?
Well, not in the calculus sense of the word, because there are no we deal in integers, so there are no real numbers. There is no really convergence to speak of in this particular for this particular problem. So what's going to happen as we're getting smaller and smaller and smaller?
Eventually, I hit to the 1 or just some number. Clearly,
So can we ever become negative? No. We cannot become negative. So we're decreasing, and we know there's a bottom there. We're going to hit at some point. Okay, so that process, seemingly infinite process, so we can repeat it and repeat it and repeat it. It actually does have an end. Okay, so that we discover. So there will be say, I don't know, P1, and then it will be larger than, so P is larger than P1, say maybe this is NP2, and so on. Okay, and then it has to be larger than 0, and then P, and then Q larger than Q1, larger than Q2, but they are all larger than 0. So the process that can be repeated indefinitely, however, has to end. So what do we conclude from this? It has to end, but it can't. So the process has to end. But it can't. Because this logic will work every time. Right? So I'm not sure if I explain it sufficiently, but you can certainly see. Let me do that. So to demonstrate that this works out for any number. So let me put it this way. So suppose. So once again, one of those lemmas that we need. Okay, so or maybe we actually can get around it probably, but suppose. So we have P1 squared is equal to 2Q1 squared. Okay? Then 2P2 squared is equal to Q2 squared. With, once again, P2 less than P1, Q2 less than Q1. Okay?
How can Q2 be less than Q1?
Yeah, I'm sorry. Yeah, I think I made two. It could. Let me. This is what I was trying to say, like this. I would have the same exact equation. So.
How can P2 be less than P1? They're the same exact thing. Like I don't.
No, this is how you build. Well, actually, I could be more specific. This is just the statement of the lemma, from which I remove the things that are really not relevant for the conclusion. But the proof is actually that P1 is equal to 2P2. That's the proof.
Yeah.
And Q1 is equal to 2Q2. That's the whole proof of the lemma, right? Okay. And now you can see how one equation produces the other, and that equation is exactly the same. There is no difference. All of those two subscripts are different from P1, Q1. We have P2, Q2, and so which means that we can do it one more time. And if we can do it twice, we can do it infinitely many times. And every time we will be declining, the size will be declining. Okay, so the conclusion is, what's the conclusion then? We have a process based on this lemma. We have a process that has to end, but it can't. What's the conclusion? What?
Impossible.
It's impossible, right? So in other words, that is the contradiction we were looking for. Okay, so at least we have worked it out. I think we have more or less all the steps that we need, and then once you start to put together the proof, other things might come up. But generally, it might be sufficient to get started. And there might be. So we had two lemmas. This one I'll just accept for as we have proven it. We haven't, but you can. So sometimes it's okay. What else do we have? We need here. We also probably not. Yeah, I think we're okay. Implicitly, we might be referring to the fundamental theorem of arithmetic. So once again, the ability to factorize might be necessary, even though just saying that n is even is sufficient. So we really don't need the full strength of the fundamental theorem. We only need concerned with divisibility by 2. Okay, so that's all there is. So, but let's once again review. So most of the proof is here. So we got to this stage yesterday, and now we can just from that we carried out. This was still analysis. We had an idea, and we tried to use algebra to see if it takes us anywhere, and we realized that it does. And now we formalize that conclusion about the repeatability of the process of the step, and it is a very simple statement, right? That lemma, and with a very simple proof. Okay, so that is very helpful. Let's try to write the proof then. So proof in the formal sense. So somebody would read it, and they don't care about our trouble and tribulations and all the work that we put into it, and the challenge of discovering a proof. It just has to look perfect, and somebody reads it, and wouldn't be asking any questions. Why is this that way or this way? They might ask how you found it, but really there should be no doubt about the validity of the proof itself. Okay, so let's try it. So what I'm gonna do is okay. So I'll just write it. Okay, so theorem. We're starting over. So square root of 2 is irrational. Okay, now I write proof, and at the end I will have put a little square at the end to indicate the end of the proof. So okay, let's start carefully. Okay, so we know everything we need to know, so we just have to put it together in a linear fashion and know, so those blind alleys that we explored, so that is also all thrown out. Well, but that's how science operates, right? So, okay, so okay, so let's take another look at it. So I think I'll do this first logical transition from this to what? To this stage over here, to this stage. Okay, and then at that point I will state my lemmas. Okay, state and prove my lemmas. Okay, so I want to arrive to that equation in the middle. Okay, so let's try to also make it as streamlined as possible. So even though we want to say every single thing, every detail to be provided, but it doesn't have to be spread out as much, which may be a bad idea in the sense that it certainly makes more work to read if you compress ideas into shorter sentences. So anyway, so suppose we know we want a contradiction. So the words that you start with, assume the opposite. So assume the opposite. So well, you can just say this is a proof by contradiction. We assume the opposite. Suppose square root of 2 is rational. Okay? Okay. Then how do you proceed from? Yeah, so then by definition, I'm writing. Then by definition, square root of 2 can be represented as a ratio of two integers. Okay. So square root of 2 is equal to P over Q. PQ are integers. Have you seen this notation? Z. What? Z stands for integers. Q not equal to 0. So can be represented. So it is represented. So this is an assumption. So can be represented. So it is represented. So we have some P and Q available here. Okay, so then once again we are put things together. I'll take the square. So let me just say it. We square the equation. So whatever you do, show it. So I have 2 is equal to P squared over Q squared, or 2Q squared is equal to P squared. Okay, so as you can see, it didn't take a lot. Whatever we did yesterday, it's all here, almost. Okay, now, so we're going to demonstrate that it's impossible. But I want to state the lemmas first. So these are the two lemmas. The first one is the simple. Odd times odd is, you probably don't even have to state it necessarily. So this is it is a judgment call. Either it is depending on your audience. Okay, depending on the audience, you may want to state it separately. So let the person to contemplate it. Maybe they see it for the first time. Okay, or maybe it's so simple then you just skip it. So let's do it. Let's suppose we are writing for somebody like yourself 3 weeks ago. How about that? Okay, so then you probably state that lemma. Okay, so lemma 1. The product of two odd numbers is odd. If you want to show how far ahead you are of that person you were 3 weeks ago, you can say, well, proof, exercise. Okay, so you say to that person, well, it's your homework. Now you should find this fairly easy, I hope. And we can move faster. But first we stated it. So any statement that has some kind of value for the future is better. You might not be either. You don't want to prove it because it's so elementary, or you think it is. You can find it somewhere on Wikipedia or something like that. But you still state it. Okay. So lemma 1, the product of two odd numbers is odd. I'll put it in the pocket, and then the second lemma is this. So just to restate it. The second lemma, that's the big one, right? So I'll just rewrite it one more time. That's no big deal. Writing is really not a lot of work in comparison to actually thinking and figuring things out. So lemma 2. So if P1 is squared is equal to 2Q1 squared. For two integers P1 and Q1, then there are integers P2, Q2, such that P2 squared is equal to 2Q2 squared. Now I'm going to prove this. So our understanding of divisibility will be pretty much hidden, concentrated in one place in this lemma. Understanding the divisibility by 2, that's pretty much, and we might need the fundamental theorem still. Okay, so we roughly know how to go about it. We did it a minute ago, so let's do it. So what's the first? How to proceed? Yeah, I forgot to. That's part of the statement of the theorem. So that you gotta so less than P1 less than Q1. So remember how we do it. Odd even once again, right? So. Well, you always use some words every time. You don't jump to equations right away. You say, observe, for example, observe that 2Q1 squared is even. Okay, then so is P1 squared. It's the same number. Then P1 is also even by lemma 1. Okay, so then I don't have to invoke definition of even. We didn't even need evenness as definition here. We just use it something that everybody knows what it means. So I say that P1 is equal to 2 P1 P2 for some integer P2, and it's going to be less than P1. Okay, substitute into the equation, original equation. What do I have? I have, well, just write it out. Once again, depending on your audience, you might show every step. So, which is really a good idea to just stick with it. So it's a 2p2 squared is equal to 2q1 squared, or 2p2 squared is equal to q1 squared. Now, at this point, so we already know that we're going to repeat the same. What the previous paragraph now will be repeated in a similar fashion. So if you want to help your reader, point it out. So just say we carry out a similar argument for the new equation. So we carry out a similar argument, or identical, frankly, for this new equation. We observe that what? Observe what? Two p2 squared is even. So I'm looking at the last equation now. P2 and so is, and then I could repeat it. If I was typing it, I would be doing cut and paste, right, or copy and paste right now. I would copy the previous paragraph and just save some writing. Then so is what is it? Q1 squared. Q1 squared. Okay. Then that's right. Q1 is also even by lemma 1. Okay. Then Q1 is equal to 2Q2 for some integer Q2, and I put a comma here. Q2 is less than Q1. Okay, and then substitute into equation, the last equation. We have the last equation, meaning at this point you can mark them with numbers. So it is sometimes helpful, you see it in books, certainly in calculus book, refer to equation 11.3.1 or something like that. So, but it's a short lemma, so it is clear what I mean by the last equation is this one, I hope. So I substitute, so I have 2p2 squared is equal to 2q2 squared, or as planned, p2 squared is equal to 2q2 squared. Okay? End of proof. This one also end of proof. It is proof as an exercise. Okay? All right, so we have these two lemmas. We have equation that we have produced from our original assumption is right there. So the lemma 1 now is forgotten. We're not going to need it anymore. So it's going to be what? It's going to be our equation and the lemma. Okay. So okay, let's try it out. So it's a narrative. So just write out what we're trying to do. What I'm saying, I could just as well write it. So we apply lemma 2 to the equation about our equation we derived from our assumption. assumption is that square root of 2 is equal to P over Q. So our equation is, what is it? 2Q squared is equal to P squared. So, by lemma, there are, well, let's be more specific. If you know, a person might be, once again, maybe inexperienced with proof, so you have to make it more clear what is that you're talking about when you say I'm applying lemma. So you say by choosing, say P1 is equal to P and Q1 is equal to Q. So you have to connect the notation that you have in your proof versus the statement of the lemma. They don't match exactly, so you have to be careful. Okay, so, but if you point out that P and Q came from the original assumption, okay, and now the theorem is about P1 and Q1, P2 and Q2. So this was supposed to be a comma. Okay, so P and Q were given, and now we apply the lemma with these particular choice of P1 and Q1. Okay, so then, by the lemma, there are integers. P2, Q2, P2 less than Q1, Q2 less than Q1, such that we have the same equation. Q1 squared is equal to P1 squared. Okay, and at that point you have to explain that repetitive process in order to indicate what's happening. So continue to apply the lemma. Producing two sequences. P1 larger than P2, larger than P3, Q1 larger than Q2, larger than Q3, and our equation is satisfied. So P, and well, like this. Remember sequences, right? So it looks very much like a sequence that we saw. We just could construct it in this manner. So Pn, Qn, okay. And then what's the relation between Pn and Qn? That is our equation. 2Qn squared is equal to Pn squared. So we have then decreasing. We actually need only one sequence to have a contradiction. A decreasing sequence of positive integers. Well, at this point, I realize that there's a flaw, and that happens sometimes in the way I stated it. So I do need the positivity of these integers, and at no point I actually mentioned that. Even though it was clear, when we did our analysis, it was clear to us that that process cannot possibly produce negative numbers. We divide by 2, but since I didn't state it, that is a flaw. Okay, so that somebody would be wondering about it. So how do I fix it? I fix it, so I add positive where it's necessary. So if we have two P1, Q1 positive integers, that there are also positive integers. Well, I put it in the wrong place. Okay, positive. Indeed, every time we just simply divide by 2, so there's no way we can produce negative numbers at any point. Okay, so then we, so we ensure that this is the case. Proof works out. Okay, so we have a sequence of positive, a decreasing sequence of positive integers, which is impossible. I could say infinite sequence of positive integers, which is impossible. End of proof. Okay. So I provided all the details. That's why it is fairly long, almost 2 pages. If you ask somebody to explain this theorem to you, they probably will do like two lines of text. And there is a shorter way to do it, and there's always a better way if you're looking for it. But if you're looking for a proof that you have a proof, okay, great, and you might try to It is a luxury if you can afford it to find the proof that is just perfect, and it can be done. And at some point we'll look into that as well. Or you may can look it up anywhere you want. So this is certainly a proof that is well known. Okay, so first make sure it's not really 2 pages. I think it is roughly 1 page. If you start typing, it's not going to be more than 1 page, right? Okay, so any questions? Yeah.
Can you go down to the end of Lemma 2?
This? Yeah. Is it?
Yeah.
It is a proof of Lemma 2. Yeah. So this is an illustration of how to find a proof through analysis, how to write it up carefully once you have everything, the question, how do you scrutinize somebody else's proof, which is what we're facing here. That is, if you can learn how to scrutinize somebody else's proof, then you can do it to your own proofs, and that is something that you have to be able to do. Well, since this is still fresh, we have a few minutes left. I don't want to start a new topic. So let's take a look at this proof. So once again, it is all here. The statement of the theorem, beginning of the proof, the two lemmas, and then the wrap-up, which has this infinite process demonstrated to us. Actually, that is a decreasing sequence of positive numbers that has to end but doesn't, will appear at least one or 2 places when you do proofs with integer arithmetic. What I want to do here, however, when you have a nice proof and it is laid out in front of you, you might try to recycle it, not just recycle it, to generalize it. So what else? How we can tweak it, the proof, and prove something more than we have proven. Square root of 2 is irrational. Anything else you can think of prove in a similar fashion?
Any irrational number.
What?
With any irrational number. No.
Well, I mean, square root of 2 is just one number. We know that there are a bunch of irrational numbers. So,
For any irrational number.
how about square root of 3? Okay, so, well, let's do square root of 3. Just let's run through the proof. That helps you to actually, digest the proof. Try to move it around a little bit. So what's going to happen if I replace 2 with 3? So, suppose square root of 3 is irrational, then by definition it can be represented as a ratio of P over Q. I replace 2 with 3, all good. That equation over here becomes 3 is equal to P squared over Q squared, or 3 is equal to Q squared is equal to, so I'll have 3 here, 3 there, right? So that doesn't change. What happens to lemma 1? Odd and even is out of the window because we're talking about divisibility by 3. So what would be equivalent of this lemma? Or maybe it might be unclear, but we're gonna need it, so we can trace our steps back. So what do you think? Unless somebody already has an idea of what lemma 1 we're going to need.
Divisible by 3 instead of even.
So state the lemma.
Product of an integer is divisible by 3 is also divisible by 3.
No. That came up yesterday, remember? You were talking about this. Odd means not divisible by 2. Okay, so the lemma would be 2 numbers not divisible by 3 multiplied together will produce a number which is also not divisible by 3. That's what we're going to need. or if you're not sure, then just proceed with your proof, and then you'll see where we use the lemma 1, and we'll realize that that's what we're going to need. So anyway, so we want to do the same procedure. We want to divide by 3. We're going to, instead of speaking of that number being even, 3q1 squared is divisible by 3, which means that the other side is also divisible by 3. P1 squared is divisible by 3. So and then by lemma 1, I want to conclude that it's also divisible by 3, and that's why I want to lemma 1 the way I put it. So I have P1 is divisible. P1 squared is divisible by 3, which means that P1 is also divisible by 3. So the way to prove it is to modify a lemma and speak of numbers not divisible by 3. So multiply those two, and it's still not divisible by 3. So that works out. To demonstrate that the square of, if the square is divisible by 3, then the number itself is divisible by 3. It's simply the contrapositive. Okay? And then I keep going. Instead of having 2 here, I have 3. I still can carry out the cancellation of 3. And for a single argument, the rest of it works out exactly the same. The lemma will be, what's the statement of the lemma? It will be, well, I'll have 3's there. Otherwise, everything works out exactly the same. So positive integers, smaller. We have, once again, infinitely decreasing sequence. This stuff works out. 2 doesn't matter anymore. I just have 3's where it belongs. And I arrive to a contradiction. Okay? So it works out. At least we outline how we do a proof. So that's a good exercise. Just take this text and prove it for replacing 2 with 3, so divisible, so that everything would still work out. Make sure that it works. But just to wrap it up, what else can you suggest? Square root of 3 is irrational. What else? How about square root of 4? Is square root of 4 irrational?
So, you want to prove that by contradiction, you would say square both sides.
Well, the answer is no. Square root of 4 is not irrational. So what's if I keep moving, what's the next on the list? Is square root of 5 irrational? Square root of 6? This one is irrational, but it is more complicated. The trouble with this one is that it's not a prime anymore. So with primes, replacing 2 with 3 is easy, then with 5, then with 7 still works out. Almost virtually no change. When you do divisibility when the number is composite such as 6, then it takes more work. But we'll look into that at some point. Okay.